graphic S will denote the grand set of applicants. This is the applicant pool. Okay. Then a choice problem is a triple consisting of a set of students coming from the applicant pool, a type function which labels each student either as a minority or as a majority type. If the type is 1, typically denoted by a red for the presentation, that means he is a minority. If it is labeled by 0, that means he is a majority. Then we have a priority ordering. For the school choice, it is just exam score rankings, which is a complete transitive and anti-symmetric binary relation over the set of students, so we do not allow any indifferences for sake of simplicity. Then a choice rule for a school with Q available seats. This is important. So we assume that each school is coming with a exogenously given capacity. Say that we have a school that has Q many available seats, then a choice rule for such a school will map each choice problem into a non-empty set of applicants without exceeding the capacity. You cannot obviously accept more students than your capacity. So the thing is that without these two extra primitives, tau and prev, type function and the priority ordering, this is the definition of the classical choice rule. The difference is now we enrich the domain of the choice rule by also incorporating the type function and the priority ordering. Since we have these market design applications in mind, we view this as a realistic, at least a reasonable model in the following sense. The question is, the type function and priority orderings are typically observable. These exam scores are public. Who is a minority, who is a majority, that is also available publicly. So since these are observable, it seems reasonable to put them into the definition of a choice problem. Now, first I will introduce the basic axioms and then the new axioms. A choice rule that satisfies these basic axioms will be referred to as an affirmative action rule. In the paper, we also refer to that as a substitutable affirmative action rule because of the importance of substance here. But for the talk, I will refer to that as an affirmative action rule. It is basically a choice rule that satisfies the following basic axioms. First, it must be a capacity filling. That is, an alternative, a student, an applicant, is rejected from a choice set only if the capacity is full. That is, if you are applying to a school and if that school couldn't fill its capacity, if there is still an empty seat, and if you apply for that, then you must be accepted independent of your exam score or independent of whether you are a minority or majority. So schools will seek to fill their capacities as far as it is possible. Neutrality, the usual neutrality notion, the choice should only depend on the types, namely whether you are a minority or a majority, and the relative priority ordering in the choice set, but not on other characteristics such as the names. Priority compatibility is, in a sense, what distinguishes an affirmative action rule from a choice rule. It requires that a student is chosen over a higher priority student only if he is a minority, but the other guy is a majority. Say that now you have a lower score compared to another person who is an applicant to a school, you are accepted, but he is not accepted. This is possible only if you are a minority. But differently, between minorities and majorities, the priority ordering, the exam score, determines everything. You can overrule priority ordering only if you are a minority, but that guy who is overruled is a majority. And the final condition, final axiom is substitutability, which tells that a student A chosen student remains chosen when the set of students shrinks, everything else being the same. Put differently, if a student is chosen in a large choice set, and if he is available in a smaller choice set, then he will continue to be chosen. This is the familiar sense alpha condition, work condition, IAA condition, independence of irrelevant alternatives condition from the choice theory. In the context of um, mechanism design, for some historical reasons, it is referred to as substitutability. Well, the first three axioms are, in a sense, well, it is still debatable, but I would say that in some sense they are natural to impose if we are thinking of an affirmative action rule, but you can say why substitutability to begin with. It is critical because of the related analytical results. The thing is that, as I said, we have in mind these market design applications, and those applications, the central concept is stability, existence of a stable matching between students and schools. And for that existence, literature shows that substitutability is crucial. That is one reason, that is the main reason that we impose it in here. And when it comes to representations, it is marriage, the marriage of substitutability with the axioms that we will introduce will play a critical role in obtaining the representations. Any questions so far?
Yes,
Okay,
I have a question.
Sure, please.
What you are saying, suppose that you have two groups. What you are saying is that it doesn't matter the fraction, the initial fraction of the two groups with this assumption. Suppose that the students shrunk, but only, let's say, white students get away from the complete set. You see what I'm saying? That there's like a fraction of the groups has some a priori fractions in the population, and probably the minority quota is related with that, and that is in some sense against this substitutability property.
So if I understand correctly, I would paraphrase that as follows. You say that there is something in substitutability which is in contrast with the idea of affirmative action. Can I paraphrase it like this?
Yes.
I agree with that. That is true. There is something that in substitutability, there is something that is tying your hands in doing affirmative action. We can think of such examples, but it is not avoiding it entirely. So in a sense, what we will show is to what extent it is possible to do affirmative action being constrained with substitutability. Okay, that is definitely right. But again, we impose, we have some good reasons to impose substitutability in here. Okay, so the responsiveness axioms, these are the comparative statistics axioms that I'm talking about. So first, intuitively, responsiveness axioms, there are two of them, they require the following. Suppose that the priority order of a chosen minority applicant is improved. He gets better off in terms of exam scores. Or imagine that he turned out to be a majority. He switched his type from being a minority to a majority. You can think of this as another problem. What do we expect after these type of changes? What should happen to the other minorities who have been already chosen? A minority is getting better scores in one case, and a minority is turning out to be a majority in the other case. We expect no other minority applicant being adversely affected from these type of changes, in the sense that if he is previously chosen, if he is chosen before these changes, then we expect him to be chosen after these changes as well. This is the basic content of the responsiveness axioms we will impose. But for the formal part, I need to formally define what do I mean by a minority applicant being improved in the priority order, and what do I mean by a minority applicant's type turning into majority. So I will give these two notions, I will define these two notions. Given a set of students S, a type function tau prime is obtained from tau by changing the type of a student S if under type function tau, student S is a minority, but under tau prime, he becomes a majority. His type is now 0. And the assumption is that there is no other type changes. All other students keep their types as it is. This is the definition of changing a type. And a priority ordering pref prime is an improvement over another priority ordering pref for a student S if, when we move from pref to pref prime, the priority order of S weakly improves relative to each other student and strictly improves relative to at least one student, while the priority relation within the other students stays the same. Basically, in both cases, we pick one student, we either convert his type into a majority or improve his priority ordering. His exam score goes up. But this happens only for a single student by keeping other students as it is. The first responsiveness axiom, responsiveness to priority improvements. In words, if the priority order of a chosen minority applicant is improved, then all other minority applicants who were chosen should still be chosen. A little bit more formally, for each choice problem, pick a student S who is a chosen minority in that problem. Then imagine any priority ordering in which student S has a higher priority, is doing better in terms of his exam score, then it must be the case that the previously chosen minorities are preserved to be chosen in the new problem. For a simple example, think of this choice problem in which we have 5 students, 3 and 5 are minority students and the rest are majority students. Say that initially we choose everybody but student 4. Now imagine that we are in another world, we are in another state at which this minority student 3 turn out to have the best exam score. Okay, everything is as it is. The ranking of 3 moved from the third position to the first position. Then responsiveness requires that we should continue to choose 3 and 5. Okay, 3 is in a sense should naturally be chosen, okay, because now he is the best guy. But this guy being the best should not create a negative externality to the other guy as him being non-chosen. Okay, this is one behavior that is ruled out by this axiom. You cannot rule out, you cannot stop choosing this, say, less successful minority because of another minority being highly successful. This is one type of behavior that is ruled out by responsiveness. The second responsiveness axiom is responsiveness to type changes. In words, if the type of a chosen minority is changed into a majority, then all other minority applicants who used to be chosen should still be chosen. Pick any choice problem, pick a minority who is chosen from that problem, and now think of a type function, think of the type function, which is obtained from the original one by changing the type of this guy. Now, since this guy is no longer a majority, is no longer a minority, well, it might very well be the case that he is no longer chosen, but this shouldn't affect the choice of other minorities. For an example, say that here again we have these 5 students. First and fifth students are minorities. And now think of another scenario in which the first guy is not a minority, but he is a majority student. Then this shouldn't change the behavior of, this shouldn't change the affirmative action as the last guy being not chosen. Indeed, it is a reason for increasing the people, increasing the minorities who might be chosen. Because if you look at the representation of minorities in the cohort, it must be decreased in this case. In the first case, we used to have 2 minority students in the cohort. In the second case, we only have 1. So it is natural to expect if there would be another minority student in here, this can only be a reason to accept him, although he may not be accepted in the first case. Again, this is the logic of responsiveness axioms. There is one thing that I have to clarify maybe at this point. As I said, we have these market design applications in mind, and in these applications, there is one critical feature. That is, schools decide on their affirmative action policies before observing these exam scores. So you cannot make your affirmative action policy contingent on these priorities. So of course, if you turn out to have a priority ordering, say, which perfectly represents minority-majority ratios, it is completely in line with the diversity that you have in mind, then there is little reason to speak of affirmative action. The assumption is that before the exam scores, as an institutional policy, schools say that they delegate some of their seats to minorities. The simplest example is in Boston district. In their public schools declare that, roughly speaking, they absorb 50% of their total seats to neighborhood students. And this is a policy that is independent of the exam scores, other orderings that can change from year to year. Now, our first result tells that a choice rule is an affirmative action rule. Namely, it satisfies capacity filling, neutrality, priority compatibility, substitutability, and as well as the responsiveness axioms, if and only if it admits a responsive reserve representation that I will introduce now. This is the general class of, this is a quite general class of representations that we introduce here. In the second part, as I said, we will focus on some simpler, more specific versions of this, which are used in real applications. So let us think of this representation in 2 pieces. First, we will have a reserved representation, and then we will have responsive reserved representation. So what is a reserved representation to begin with? Well, it is in some sense the most natural thing that you would do if you are about to implement such an affirmative action policy. Say that you are a school that has a capacity of Q. Then here is your policy. At each problem, first of all, you choose all the minorities who are top Q ranked. So first of all, forget about minorities and majorities. If there wouldn't be any affirmative action story, if there is no minority at all, then the most natural thing for the school is to pick the top Q best guys according to their priority ordering. Okay? But now we have minorities, which is the target of this affirmative action policy. And if a minority is already one of those top chunk guys, if he is one of the best Q-ranked person according to the exam score, he should be immediately accepted. That is done. Okay. Then comes the affirmative action, the real affirmative action story. Now think of the bottom chunk students, namely students who are not one of those top Q ranked students. If you are a majority in this bottom chunk, you have no chance of being chosen. Okay? Only if you are a minority student who is one of these non-top Q ranked students, bottom chunk students, then you have a chance of being chosen. But how many of them are chosen? That depends on the reserve number that the school decides depending on the problem. Indeed, reserve number quantifies the intensity of the school for implementing affirmative action. He can say that this group of minorities need real help, so I will keep the reserve number big, or they do not need that much help indeed, so I am going to keep it as a small number. Okay, but notice that
sorry,
this.
Sorry. When you the certain number of non-top Q rank minority students, that's the reserve that you have in mind, and it should be independent
Exactly.
of the particular applications of the students, right? That's
the point that I was about to make. As it is entirely, it can depend on the priority ordering. It is very
right.
general, but notice that it is not the representation that I get. I need some additional constraints on this representation. This is the most general, unstructured representation that one can think of, right? But as I think you notice, it is too general, it is too ad hoc, okay? This reserve number can change in an arbitrary way from problem to problem. That is the problem. That is why we put these responsiveness axioms, and now is the time to discover the implication of these responsiveness axioms on this general representation, as well as the other basic axioms, not only responsiveness. We don't even have substitutability in here. Such a reserve representation can potentially violate substitutability as well, in a very simple way. Okay, so it is quite unstructured. Now, here is what we observe. Here is the responsive reserve representation that we suggest. It additionally puts two requirements on a reserve representation. First, this reserve number at each problem should depend on the type configuration of the top Q ranked students, on the type configuration of the top chunk students, minority, minority, majority, or majority, majority, minority. Only these type of configurations for the top chunk matters. Bottom chunk does not matter at all. The names in the top chunk does not matter at all. The only thing that can matter is whether a minority is first ranked, second ranked, third ranked, so on and so forth. Okay, but not only that, the second one is more interesting. The second requirement is that I would call it like this. I would motivate it like this. It tells in a sense that this reserve number cannot change drastically from problem to problem. It should respond to changes in the problem in a continuous way, in a moderate way. Meaning that the reserve number changes by at most one in response to a priority improvement or a type change. Say that for a problem we have 5 reserved seats. And imagine that in that problem, just one guy, one minority guy, increased his position by 1 position. He just moved on top of the next majority guy. Reserve representation allows to decrease my reserves into 0 or to increase them into 10. Responsiveness tells that you can't do it like that. You can only respond to these type of changes by increasing your reserve number at most by 1. Okay. The same thing with the type change. Say that in moving from one problem to another, one minority student turns out to be a majority. Then you can increase your result number at most by 1, not by 2, not by 3. Okay, so in a sense, this is sort of an unexpected structure that would come from the type of axioms that we impose. Our axiom has nothing to do with these numbers, but they just pop up mainly by the marriage of substitutability and responsiveness. Let me show you an example to get a better understanding on what sort of representations we can have. Say that we have the grand set of applicants have, say, 6 people, 6 students, and the capacity of the school is 4. Now, I will denote the top chunk configuration by this row. So a row tells minority majority configuration of the top Q ranked students in a problem. So here is one reserve rule. Suppose that in the top chunk, there is no minority student. If there is no minority student in the top chunk, my rule is going to reserve 2 seats for the minority. I will pick 2 minorities who are not in the bottom, who are not in the top chunk. Okay. If, on the other hand, we have 1 minority student in the top chunk, then I will reduce my reserve by 1 and I will pick 1 guy from the bottom chunk. Notice that from moving from I to I, my reserve changed only by 1. It didn't change in a drastic way. Now, the thing is that I can do some more colorful things with a responsive reserve representation. Say that in the top chunk, there are 2 minorities, 1 and 2. And suppose that 1 has a better ranking than 2. Now, I can say that if the best minority is not top ranked and the worst minority is at the 4th rank, that is, the last capacity that I have, then I am not reserving any seats. Okay, so in a sense, I am thinking that, look, I already admitted 2 minorities and they are not so good. The best one is not the best, and the worst one is really worst, is barely acceptable for me. In this case, I'm not reserving any seats for further minorities. But if this is not the case, then I am going to reserve 1 seat. I am going to pick an additional minority from the bottom chunk. This sounds quite arbitrary, I agree, but this is something that is allowed by this responsive reserve representation. And finally, just to complete the example, if in the top chunk I have 3 or 4 minority students, I am assuming that there is no reserve seat at all. Interesting thing is that the important thing is that these reserves are not changing drastically when we move from one type configuration into another. Here there is no minority and I have a reserve of 2. Here there is only 1 minority, I have a reserve of 1. Here I have 2 minorities, my reserve is either 0 or 1. And here my reserve is 0. This no drastic changes in the reserves is the structure posed by the responsiveness axioms and the basic axioms. Okay. Now, here is one thought experiment if you want. In our next result, I will in a sense argue that responsiveness is necessary, is in a sense necessary if you would like to have an affirmative action policy. Here is what I mean. Now let us think of the opposite of our responsiveness conditions. Namely, think of negative responsiveness to priority improvements. If the priority order of a chosen minority applicant is improved, then suppose that all the majority applicants who used to be chosen should still be chosen. In the context of these, in the following story, indeed, one can argue that this is an appealing condition. Suppose that as a school, I decide on my reserved seats after observing the ordering. Okay, if this is the case, then you can say that since you have a target of representation for these minorities, then once a minority applicant's rank is improved, that means they do not need that much affirmative action at all. So why are we killing the seats for the majorities in such a case? Okay, so a minority doing better and better is a signal, can be a signal for not doing any affirmative action. Okay, then in this case, one can argue that this type of an axiom is appealing, is reasonable too. Similarly, we can formulate negative responsiveness to type changes, telling that if the type of a chosen minority applicant is changed into a majority, then all the majority applicants who used to be chosen should still be chosen. Now we show that under a very mild assumption. The assumption is that suppose that in the grant pool of applicants, we have at least Q students, it becomes a mess because of some simple technical problems. And let C be a substitutable affirmative action rule. Here it means just an affirmative action rule. Okay, it's a choice rule that satisfies the basic axioms, not the responsiveness axioms at all. Then suppose that C satisfies negative responsiveness to priority improvements. Then it must also satisfy responsiveness to priority improvements. Similarly, suppose that C satisfies negative responsiveness to type changes. Then it must also satisfy responsiveness to type changes. Okay, so what does this mean? Negative responsiveness and responsiveness are quite the opposite. That means if a choice rule, if an affirmative action rule satisfies negative responsiveness to priority improvements, then it must satisfy invariance under priority improvements, which tells that if the priority order of a chosen minority applicant is improved, then the set of chosen applicants remains the same. We improve a minority, nothing changes. That is the marriage of, that is putting responsiveness and negative responsiveness together. Similarly, if the type of a chosen minority applicant is changed and he remains chosen, then the set of chosen applicants remains the same. That is the intersection of responsiveness and negative responsiveness. This is the only way that an affirmative action rule can satisfy negative responsiveness. So basically, you can read this as an impossibility result. There is no affirmative action rule, a rule that satisfies the basic axioms and that satisfies these negative responsiveness, with a strict instance of, I improve a minority applicant, but an additional majority applicant is chosen. Such a thing cannot happen. It is not the only point. It is these invariance axioms naturally come from the marriage of negative responsiveness and responsiveness, but please keep them in mind. They will serve an interesting purpose in the rest of the talk. Now, I'm moving to the second part of the talk, in which I will introduce choice rules that are used in practice. They are typically what is called lexicographic rules. In terms of applications, if we go to school choice applications in Boston and Chicago, we see them. If we go to choice rules for Indian governmental job positions, we see them. In visa applications in US, we see them. In Israeli army branch matching, we see them. Okay, these applications have different details, but the lexicographic feature remains in common. Different versions of a lexicographic rule is applied in these, and the question is, okay, which one is serving the purposes better? That is a mystery in some sense. There are some empirical studies on that, which have been very successful, but there is no theoretical analysis. Put differently, one cannot argue based on some axioms, some principles that one is doing this and the other one is doing that. That is, I think, one of the implications of, we hope that that will be one of the implications of what we have done in here. Now, to describe the lexicographic choice rule, take a problem. We have a given priority ordering. Now, from this priority ordering, we will obtain an affirmative priority ordering by simply moving all the minorities to the top by keeping the relative rankings as it is. Okay? And then a lexicographic order assigns, this school has Q many seats. Okay? It has a capacity of Q. It has Q many seats. A lexicographic order assigns, a lexicographic order labels each seat either as an open seat or as a reserved seat. If it is an open seat, it will accept an applicant by looking at the priority ordering directly. If it is a reserved seat, then it will accept an applicant by looking at this affirmative priority ordering. Which of these seats will be reserved as open or reserved is what is determined by the lexicographic order. Okay? An open seat is to be allocated based on the priority, and the reserved seat is to be allocated based on the affirmative priority ordering. Let me show some examples which would clarify the representation. Suppose that we have 5 students, capacity is 3. Say that my lexicographic order does not have any reserved seats. It says all the seats are open seats. Okay? That means I have 3 orderings which are identical to the priority ordering. First, I go to the ordering for the first seat. On the top, I have agent 1. I choose him. Then I go to the second seat. On the top, I have agent 1, but he is already chosen. So I choose the next guy, which is agent 2, student 2. And for the third seat, again, I look at the priority ordering. I have already chosen 1 and 2. That means 3 is now on the top, and I am choosing that. It is no different than just directly accepting the top 3 ranked people in here. But now suppose that I'm reserving the very first seat as a reserved seat. This means what? 1 and 5 were the minority students in my problem. And in this ordering, 1 and 5 comes at first. In the first seat, for the first seat, I am choosing agent 1. For the second, I choose 2. And for the third, I choose 3. The interesting thing is that although I have 1 reserved seat, the set of the choice set didn't change at all. Okay, so I can think of another lexicographic rule in which this time the reserved seat comes at the end. So first I choose 1, then I choose 2, and then for the third seat I choose 5. This time I accomplished choosing an additional minority. As the simple example demonstrates, reserved seat coming at a later stage provides some additional advantage for minorities. And in general, with 1 seat, things are simple, but the position of these reserved seats matters a lot in terms of what is the implication of the particular lexicographic choice rule for the affirmative action policy. So in general, we say that a choice rule admits a lexicographic representation if there is a lexi order such that for each problem, we obtain the choice by running this lexicographic procedure according to that order. There are 2 special cases which arise a lot in the applications. One of them is the reserved first representation, in which all the reserved seats precede the open seats. It is one of the examples that we have seen. And the other one is the reserved last representation, in which all open seats precede the reserved seats. And now, what is the link? What is the connection to the general class that we have characterized? Lexicographic choice rules is a special class of the responsive affirmative action rules that we have already characterized. So this is a special representation, an example of a responsive reserved representation, but it is indeed a very particular one. Here is the thing. Here is the second result. A choice rule C is an affirmative action rule that satisfies invariance under priority improvements if and only if it admits a reserved first lexic representation. C is an affirmative action rule that satisfies responsiveness to priority improvements and invariance under type changes if and only if it admits reserved last lexic representation. So we characterize a general class of plausible choice rules for affirmative action policy, and in a sense, the most popular to subclass of these rules turn out to have a simple characterization, turn out to have a characterization with an edge axiom that we have, that is invariance axioms. That is the message. We believe that this result, in a sense, sheds some light on why these two specific lexic rules are so popular for these applications.
Kemal, just to see if I understand, like the first characterization of this kind of reserved first lexicographic representations seems, okay, maybe I'm wrong, but I think that Echenique and Booming Genmes, they have the characterization related to this one, no?
Exactly,
but
that is definitely true. But the choice model is different. The formulation of the choice problem is different. Therefore, the axiom that they use is saturated priority compatibility, I would say. It's a different flavor. We have an entire section on that discussion. You are definitely right. We have an intersection with Echenique and TMS when it comes to reserved first lexi. Other than that, I would say no intersection in terms of lexi. But with reserved first, we have, however, the axiom is in a different flavor. It's telling something else.
Right, no, and they really go after reserve first. They don't really have anything about reserve last, if I understand correctly,
exactly.
right? So that's, I see.
And on top of that, once you come to that stage, although in terms of the applications it is debatable, but for theoretical curiosity, one question is: can we axiomatize the set of entire lexicographic choice rules? Say that this order does not have any structure. This reserved open sequence can be in any arbitrary way. You have to be careful when you ask these type of questions. Otherwise, it can take 3 months out of your life. It happened in this case.
Kemal hocam,
still, we are happy with the results. Okay, I think I can summarize this part and then I will finish. Thanks. So I would like to briefly give you the general representation for the lexicographic choice rules. For this, we need to introduce one notion, that is a type change or a priority improvement being effective. Here is the thing. Take a problem, take a chosen minority. Suppose that we have changed his type. Then we say that this is effective if it results in new chosen minority students. We know that because of responsiveness, chosen minorities should continue to be chosen. But the question is, if a new minority who wasn't previously chosen turns out to be chosen. If that is the case, we say that this type change is effective. Similarly, we say that a priority improvement is effective if improving the priority of a chosen minority results in new chosen minorities. Then with this notion, one reasonable axiom is to put some sort of monotonicities. That is, if changing the type of a chosen minority student is effective, then a following change in the type of a lower ranked chosen minority student should also be effective. If you are changing the type of a third ranked minority student, and if this leads to some new minorities to get chosen, then if I change the type of a lower ranked, say 10th ranked chosen minority student, this should also be effective. Okay. Similarly, monotonicity in priority improvements require that if improving the priority of a chosen minority is effective, then a following change in the type of a lower ranked chosen minority should also be effective. This time I'm not changing his type, but I'm moving him to the top. I'm moving him up and changing the type of a minority student who is lower ranked. Okay, this should also be effective. The argument is this monotonicity. If the first one is effective, and the second one should also be effective, because in terms of the intuition is that in terms of making minorities worse, the second movement is a more drastic one. Well, these monotonicity axioms, together with responsiveness axioms, give us the characterization of entire lexicographic class. So a choice rule is an affirmative action rule that satisfies the responsiveness and monotonicity axioms if and only if it admits a lexicographic representation. And the interesting thing is that this part, as a choice theorist, this is something that typically does not happen. This representation is unique. So when it comes to identification, it gives a crystal clear picture. Conclusion. As a student of Ariel Rubinstein, I'm in the tradition of not making any conclusions. I can add that one reason for that is I always get the feeling that I get from Escher's paintings from our conclusions in economics. We typically repeat things that we have already said somewhere else in the paper. So instead of a conclusion, I'm leaving you with a representative picture of that.
Okay, thank you, Kemal. Thanks a lot. Are there any questions?
My pleasure.
So, okay, thanks to all the participants. And I mean, this does not surprise me that, again, it's a very original, modeling of a well-known problem. Thank you. Thanks a lot, Kemal.
My pleasure. Thank you. I'm flattered. It's a pleasure for me. Bye.
Bye-bye.
Thanks a lot. Bye-bye.
Thanks a lot for all the questions, comments. Bye.